Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Well, thank you very much for coming here, and thank you for persevering. It's going to be useful. As you saw, we were having some network connectivity problems, but we got it right, and so we should be able to see a good demo. It's a great pleasure for me to introduce Professor Agrawala to you. I will not read out this whole bio because you already have that. I will just point out a couple things. One, I don't know if you know, but Professor Agrawala is the father of Manish Agrawala, who was a professor, who was a researcher in MSR for about 3 years, and now he's gone to Berkeley as a professor. And he got his bachelor's before I was born, and before many of you were born as well. So he's been around. He's done a lot. Another thing I'll point out is he has published 7 books, has published 240 papers. So quite a feat. He got his PhD degree in applied math from Harvard University in 1970. He's a faculty in the University of Maryland since 1971. And he's done a whole lot of stuff. I mean, location is just one aspect of his research. I was talking to him this morning. I've learned about many things he has done. So if you're going to be meeting with him, ask him about all the other stuff he's done. So with that, I'm going to hand it over to Professor to tell us a little bit about the system that they have been building and he's building.
Thank you, Victor. First of all, let me also thank you for persevering with the technical difficulties with the networking that always happens whenever you try at a different location. Only comment I can make about what Victor was saying about papers and books just goes to show that I'm old. That's a different way of saying it. And it is indeed a pleasure to be known as Manish's father. So to some of you, I can tell you that story separately. Anyway, it's a delight to be here. Victor and I have been trying for about over a year for me to come here, and finally I am here. What I'm going to do is to share with you some of the kinds of things that we have been doing lately, and the title is Location, Time, Context, and Systems. Main purpose of this slide is, of course, so that you can spell my name, which I shouldn't worry about because a lot of you have spelled Manish's name. One of the things that I've been looking at for a while is what kind of systems are we looking at when we go to tomorrow's environments, where the compute power is becoming extremely inexpensive. The communication capabilities are expanding at exponential rate, modulo the glitches that we run into now and then. So what we are trying to do is to find ways by which we can more effectively support people, integrating variety of information sources. And key, I think, in that is providing appropriate information as, when, and where it is needed. When, time, where, location, and the rest of it is context. So that's what my talk is about in some sense. Now, clearly a number of scenarios you can talk about in this context. To this audience, I'm not going to try to motivate those except to tell you that the thing that we have been doing have been related more to, started out with our first motivation from the first responder type of situation. And in that, we put together a system we call Draco. A little bit about its history. It's basically a self-configuring, rapidly deployable communication network which supports voice, video, telephony applications, has a click and connect feature. But how did we get to it? All of us remember 9/11, 2001. Within 2 weeks after that, there was a major destruction that took place on the University of Maryland campus. There was a tornado where a car with a couple of students was lifted, went over a 6-story building, dumped on the other side. Lot of other destruction took place. And the key thing that we were hearing in all of these situations was that the first responders don't have good ability to communicate, to integrate information, to know the situational awareness, etc. So It just so happens that we have been working on Rover system as an integration platform, but we put together this Draco, which was implemented in the middle of the field on this campus out here, which was having basically self-contained access points with their own battery backup and solar panels. They were connected via over-the-air laser to the internet connection. The endpoints at that time were these two type of client devices. And our goal was to have this kind of system up and running in half an hour. We had it up and running in about 5 minutes. And that 5 minutes was the time it took for people to run around and turn the access points on. After that, it was a matter of seconds that it came up. What we had done was to invite at that time, remember we are in Washington, D.C. area, so we had invited many of the agencies from the area, some of which refused to identify who they were for obvious reasons. And the basic thing was, can we have this system tomorrow? We are a university, so we demonstrate feasibility. And so we went on and moved to the next phase of it, which was Draco 2, which was demonstrated 2 years later. And in this, the key thing that we were trying to do was have a commander's console on which we could display the scene scenario, and then as the different firefighters or responders were going in, keep track of each of them, have sensors with each of these firefighters whose information would be coming back. We could have off-site sensors also, like there are some sensors which can detect from a distance the presence of dangerous gases, and that could be integrated. That's the kind of system that we were putting together. By the way, have any of you seen actually how the firefighters work? Most of them. Until a few years ago, the most advanced technology that they had for managing the fire scene was a whiteboard. And they had advanced from a blackboard to a whiteboard within the previous decade. And the typical thing that the scene commander would do is have a Velcro tag to know who has gone in and who has come out. The typical kind of thing about the emergency situations was that if a firefighter does not move for 30 seconds, there's a shrill alarm that comes out. That within the last few years has been changed, that it now sends electronic signals that can be detected. So the situation basically had been very, very primitive. And our issue was, what can we do to actually take this kind of technology and bring it to the current use in first responder? And then there are many other uses that we can have. What I'm here to talk about more is about the integrational platform that we had, which is Rover, which was the one that supported the first version, which was implemented in 2001. It was based on Linux, which was the primary basis for Draco. And in this, the basic idea is that you've got, it is effectively an information level switch that you can say, which keeps track of all kinds of context and information. So here is the Rover controller or server, which can be connected to a variety of databases, to a location server. There can be, via base station, a variety of devices that are connected. The connectivity, the way they are connected, is not important, because main information exchange and management is done from here. And it is designed to be a distributed implementation, so you could have it at multiple different type of places. That was the basic structure of it. Current structure. Let me show you where we are today. What happened? What I have here is a connection which is going back to the building in which we do our primary testing, like you guys do on your MSR campus. At least one person in the audience can recognize that out here, this is where my room is, and this is where my students' room are, and what you see as dots are a couple of students that are moving around there. What I have also done before I turned it on was to get the voice connection going, and that's the sound that you are hearing. And we can see Elvita. Are you there? Hello?
Hi, we can hear you talking about Elvita.
All right, okay. So what we are doing here, right, what we have implemented in this is the location type of situation, and there are two devices that are moving around, and I'm going to put a tag here and say, please go to it, place tag, and the tag turns brown, and if somebody doesn't get there in 30 seconds, it will turn red. The basic idea of this was to emulate a search and rescue type of mission. So the search team comes in, and wherever they find any kind of item that requires attention, medical emergency, hazardous material, or any other, they could leave a tag, which is strictly a virtual tag in the system. Nothing physical is left there. And then when somebody gets there, they would turn that. Looks like Rome 1 has failed, you guys. One of the constant properties of any demo you give, Mr. Murphy works overtime on demos. But what you're seeing here is the corridor, which is basically this corridor. So even though this unit has failed, now it got disconnected. But he got to that, and he picked up that particular tag and changed its status. In fact, both of them have converged to that. The basic thing that I wanted to show in that this demo is that we can, by clicking on any of the icon, establish an audio and video type of a connection, which we are doing right from here and talking to them. We have this kind of tagging capability where we can leave tag, they can leave tags for each other, for the overall system, and all these tags are virtual tags which are just kept track of within the system. You can also monitor. Right now we are not leaving the tracks for the people as to where all they have gone, and as we leave the tracks, you can also cover in search and rescue type of mission what areas have been covered, what areas have not been covered. This is one of the demos that we have of this. Clearly you can incorporate this in a variety of scenarios, variety of situations, whether you talk about hospitals, you talk about airport securities, any of these kinds of things you can do. Anyway, guys, I'm going to turn off the demo here, okay? They can continue to listen if they want. What happened here? I must have been clicking away at this. One of the things that comes up in this kind of situation is that you do want to be able to integrate a variety of things. Like in this, there are there are various kinds of location technologies, various time kinds of technologies that you may want to integrate, various knowledge bases, sensor technologies, etc., etc. So one of the things that we are trying to do with Rover is to come up with a really flexible integration platform. But for that you require various kinds of these technologies, and what you see colored are the kinds of things that my group has built. What you're seeing in this demo were the location was using Horus, which I'll talk about very shortly, and Rover was the platform on which this was integrated. Those were the technologies that were integrated on this. Anyway, moving right along. So enabling technologies in this are for location, where we have worked on a couple of them, for time, and there we'll talk about some clock synchronization, and then finally we'll talk about the Rover as the integration platform. So let's get into location technologies. And in that, one of the things that we require for the systems of the type that we are talking about is that we should be able to get accurate location indoors and outdoors. Normally, whenever you use the word location, people talk about GPS, and GPS has its own limitations. That's all I can say. I mean, here people have been working on location technologies for a long time, so I don't have to sell the idea of getting indoor location. The accuracy of the location that we get depends a lot on the kinds of applications that we have in mind. In certain class of applications, we want to be able to distinguish two people sitting across a table, or two people standing in front of an exhibit at a museum, or two people working on a patient in a hospital. In others, knowing just which room you are in a building may be good enough, or which building you are in on the campus may be good enough, or which campus you are in a city may be good enough, and in some, which city you are in may be good enough also. What we have been doing is trying to go after indoor location, and in that we have been working on a couple of technologies. Another issue that comes up with that has to do with rapid deployability. how quickly can we erect so that we can then get the location. For example, when we talk about the firefighter scenario, expecting that the building in which the fire is caught has pre-calibrated type of signal strength measurements is a little unrealistic, or expecting firefighters to create a radio map when they go in is even more hazardous. So we want to be able to deploy that very rapidly. Another requirement, and clearly it has to be robust against temperature, against failures, faults of a variety of types. The two technologies that we have been working on, one is called Horus, which is based on signal strength, and second one is called PinPoint, which is based on time of flight measurements. So let's go to each of these. Horus Technology first. We learned this game from Victor. He's the one who first published the radar, and the kinds of things that we are trying to do is to follow up on that. But what we find is that the signal strength varies very, very rapidly. Here on the right, what I'm showing you is these distances. This is in inches. So across 21 inches on this side, 12 inches on that side, this is how much the variability that you have. What we have is a big mess at our hands when you just take a look at the raw data. We find that it does not follow any free space loss type of formulas that we see published in the books. So we go to the radio map type of characteristics. But then there are temporal variations, which can be from one access point or multiple access points. And then spatial variations, large scale or small scale. Let's take a look at them. From one access point, sitting at one location, we get signal strength measurements that vary over time over this kind of range. Nice histogram. But what has changed? Nothing. The access point is transmitting at the same signal strength. The receiver is at the same location. Why is this variation coming in? But it does. If we take a look at across multiple access points, we notice again a lot of variability, and what we find is that this 85 or this is 80 is typically this sensitivity that is set minus 80 dBm. So you get very little signal strength across that. Temporal variation. This is an interesting one that we found, that as we take a look at the measurements, successive measurements at one location, there is a high degree of correlation. And if you see what we have done here is this curve is for this part expanded. There's a nice decay, just showing a high degree of correlation. What that implies is that if you assume that your measurement values are uncorrelated, you run into problems. One of the key, and this is the spatial variation over longer distances along one corridor, doesn't have a monotonic function of distance. Why does this come about? Because of multipath and other kinds of effects, I guess. And this you have already seen what happens in the short distances. And this is clearly because of multipath kinds of effects. What we did was to reflect in our design as much of the detailed characteristics of the signals as we could, and most of these results have been published, like the basic algorithm, then correlation handler, continuous space estimator, etc., etc. I can give you details of all of these or the pointers to it. In the basic algorithm, what we are doing is in the offline phase or before deployment, we go and make the measurements at these different points and create the histograms. And in the first base, yeah, question.
Can I ask what may be a stupid question? So all the characteristics of the environment you're showing us, I assume they were taking in a living and working environment.
Yes.
So do you have a sense whether it's any different in a disaster area where all the other sources of interference have, I don't know.
I can tell you I have not made any measurement in a burning building.
Okay. Well,
No, that was a light-hearted answer. The serious answer is that I really don't know. I don't know. The other reason why I don't know is that, or I will not even try, is that this approach is not feasible for those kinds of rapid deployability type of situations. I'll show you the other technique which will work. Okay, but this one you cannot go to those kinds of disastrous environments. Now, in certain places like in an airport, you could do that. In a hospital, you could do that. And there, if some emergency situation comes up, yes, you can provide this kind of support. Yeah.
If I want it to be even worse, an adversary could start actively, sending out an active jamming signal or something.
True. Yes. So there are those kinds of situations that you have to worry about also. And I mean, simplest thing is turn a microwave on. Your Wi-Fi is dead. So there are various other such kinds of things that you could do. Now, in this one then, and first basic thing that we were doing is in online phase, do simple, straightforward Bayesian inference. So at 2 different points, you have the 2 different histograms. You calculate the probabilities and then say that the person is likely to be next to that. Then using multiple samples, I'm trying to rush through because there's a lot of ground I have to cover and I've already lost some time. But if you have any questions, don't hesitate. We can talk now, later, as the case might be. We need to average multiple samples to increase accuracy, but the independence assumption is not quite accurate in that. And that's because of this correlation that we have already seen. So we created an autoregressive model, estimate the correlation degree, take that into account, and that improves our estimates. When we are doing the estimation, we are going to these specific points where we had made the measurements, but a person can be in between. So we have continuous space estimator in which we are using center of mass of the top ranked locations and time averaging window where we are taking the average of the places where you may have been. That's the kind of thing that again brings about improvements. Then small scale compensator. We know that this signal strength varies very rapidly nearby. So one thing that we did was to perturb the signal strength vector by small amount. And then of all these measurements that you choose the value which is closest to the received signal strength and thereby then estimate the, improve the estimator on that. Then location clustering, all we are saying is that if in an area we know that only few access points are to be heard, just reduce your estimations on the basis of that. These are the basic components that we have of the system. In this, we start out with basically using the device driver from which we are doing the signal strength measurements, and this is sort of the offline phase where we do the clustering, radio map building, correlation modeler, and then construct the radio map and clusterer. At the runtime, we acquire the signal strength, go through this path, and ultimately come up with the location. So that's how we are implementing this. This is just animation. You're going through all these steps, I guess. So the test bed that I was building on is the A.V. Williams building where my office is. And these are some of the raw parameters. You're using UMDNet, which has Cisco APs. There were 21 APs. 6 on average could be seen from any location. Did measurements at 172 locations, which were 5 feet apart, using Windows XP Professional. We also did a comparative assessment at another building, which was of Fujitsu Laboratories, who were a collaborator for some time. And here are some of the parameters on that. Then we did later estimation. Anyway, so these are the comparisons, and with my due apologies to Victor and others who have worked on radar. This was our interpretation of the published work on radar a few years ago. And what I can point out here is that the average error that we got when we incorporated all components was about 1.38 feet, which was, I think, pretty remarkable for the kinds of mess that of the signal that we are handling. And radar, by the time you incorporate Horus techniques, that gives you significant improvement in performance also. So we'd be glad to share all these with you if you wanted to. Anyway, let me move on and talk about another location determination technique we call PinPoint. Yeah.
So I had a question about scalability on this. How long does it take to, say, calibrate the system with about 10 access points?
The number of access points doesn't matter. What matters is the number of locations at which you are making the measurements. What I was showing you in the demo earlier, where these people are moving around and going from place to place, we made this calibration Monday evening. because last week our IT folks had changed all the access points on us. And this was done about 20 feet apart, primarily along the corridors and in some of the offices. And in doing so, it took 3 people about an hour's time to complete the complete calibration.
So there are how many points are there?
I don't remember the exact number.
Okay.
Yeah.
But do you have any latitude information there as well, or just? I mean, can you also locate people in terms of like which floor?
Yes, yes. Typically, we have calibrated 3 floors of that building, 2 floors of that building, and we can tell you which floor you are on. The next step in this is that we will be calibrating the complete building and the outside area. And the general plan is that in due course, we expect to roll it out campus-wide. And our campus has a total of about 2,200 access points, about 70-some buildings, and large area.
And this is using all off-the-shelf components.
All off-the-shelf components.
Everything existing. Okay.
Right.
Excellent.
Only trouble that is there in that is that so far the stable NIC that we have found is Orinoco NICs, and now it's difficult to buy those. And when you buy those, they're using different chipsets, so they're not as good as the old ones were. So maybe we'll have to go to eBay to buy or what have you. Okay, any other questions about the signal strength based stuff? One of the limitations of this signal strength based technology is that you do need to do certain amount of calibration. So another technology we have been looking at is the time based. And when you go to the time based, what you're trying to do is to measure the time it takes for signal to travel from point A to point B. And even going at speed of light, in 1 nanosecond you only go about 30 centimeters or 1 foot. So depending on how accurately you can measure the time, you can get the distance measurement. And one of the basic limitations that you run into in that is that of clock synchronization. When you use synchronized clock with GPS, they tend to be expensive, and the accuracy of synchronization that you get is of the order of a microsecond from what I understand. Remember, a microsecond is equivalent to 1,000 feet. So in many of the environments that doesn't quite work. When you use echoing, then you have round trip time measurement, and it has its limitations. You could use cricket type of situation where you use RF for synchronization and then ultrasound for ranging. We have, of course, expert on cricket here, so I'm not going to say anything more. But then we have our thing, which we call PinPoint, which is time of arrival based. It can be software only solution, can work with standard protocols like Wi-Fi or WiMAX. No calibration is required, no synchronized clocks are required, no echoing is required, efficient in terms of constant number of messages per node to locate all other nodes, a few feet accuracy, work both indoors and outdoors. Sounds like a salesman's talk, right? Basically what we are doing, and I'll go into some details of this right here, we have 3 phases: the measurement phase, information exchange phase, and computation phase. In measurement phase, each node transmits a message containing its ID and the transit timestamp of the message. Our basic assumption in this PinPoint work is that every node is capable of time stamping, either sending or receiving messages, and the time stamping is done with respect to the local clock, which is free running clock, not synchronized with anything, and the accuracy that we give you of the location is primarily tied to the accuracy of the time stamping that you have. So each node transmits, all receive and record the received timestamp of messages sent by other nodes. All messages are strictly one-way messages. So what basically is going on, that this node A is sending, node B is receiving, node B is sending sometime later, node A is receiving, and the process is repeated. So this first cycle and second cycle. So then in the information exchange phase, which is the next one, each node transmits a message containing the received timestamps by other nodes in a measurement phase. So basically, the sending node has the time, this tau A1 when it's sent, receive node has the time tau B1. Later he'll send this back to this guy in the information phase. Or in other words, each node has the send and receive timestamps for all the messages. And these are order n messages because each node is transmitting while all others are receiving. Then each node computes the spatial coordinates and clock attributes of every other node and get accuracies of this type. The key thing that's involved in this is that we are going with a basic model of the clock where the local clock time is related to the real time through these two parameters, the drift rate and the offset. And what it does is, based on all of these, we can calculate beta b times d at any and every node as the distance measure, and we expect that beta b is of the order of few hundred parts in a million or 10 to the minus 4 type of numbers, 1 plus or minus 10 to the minus 4. So this is a very good estimate of distance. That's the key thing that's involved in this particular approach that we have. So one thing that we did do was to build some hardware. And mind you, as I was mentioning to Victor earlier, in my group the only one who knows how to burn their hands on soldering iron is me, and I haven't done that for 25-30 years. So we tried to find somebody who actually in his basement built this circuit, where he used some FPGAs, and we could get on Altera, in fact next slide has some of those details, Altera 1C20 FPGA with this kind of a radio, and this was for information exchange. And the kinds of things that we did on that to evaluate, we used indoor and outdoor test bed and did a mobility test. These are the actual measured numbers. This was with the clock, which was 3 nanosecond clock, because on the Altera the fastest clock we could implement was a 300 megahertz clock. And these are the perfect versus measured values of distance where this was a controlled type of environment. Yeah.
Why did you have to use like custom hardware? Like why couldn't you just use hardware timestamps on those two parts?
Yeah, I wish we could, and I would strongly urge you and anybody else who can provide us with that kind of hardware to do that. The standards of Wi-Fi call for 1 microsecond timestamp. Remember, 1 microsecond is 1,000 feet. That's where the difficulty is. Now, the fact is that in most of these NICs, the base clock is at 40 megahertz or 80 megahertz, and I'll come to that very shortly. But they're still giving you timestamp at 1 microsecond accuracy. That's why I couldn't. Yes, sir.
Well, is this an 802.11?
802.11, yes.
Homemade hardware.
What we did was to use the Maxim chipset for RF transmit receive. The technology is totally agnostic about what communication medium you're using. All I need to do is to send you an event, whatever you call that as an event, with a timestamp, and you timestamp when you receive that event. Okay? I'm not concerned about the modulation technique you're using, not concerned about the frequency spectrum you're using, any of that. So in this one, we had taken certain shortcuts, like we were sending some square waves at fairly low frequencies to actually demonstrate the feasibility of some of these ideas. Yes, sir.
Are there any assumptions about radio connectivity? Can everybody hear everybody else? Or
if they don't, we have multi-hop kinds of things. But see, what's happening is that whatever is the group that is doing the actual sending and receiving, that group will be able to measure the pairwise distances. And then it's a separate well-known trilateration problem, that if I give you a pairwise distance between a set of nodes, can you lay them out in 2D or 3D grid? And then if there are non-overlapping, then how to do that? In fact, the gentleman who worked here, Adele, his PhD dissertation was on that problem. Yeah?
This is related, but so if you had only 2 nodes, it seems like we would have more unknowns of equations in this. So is there
if you have, yeah, see, if you have only 2 nodes, then all I can tell you is the distance between those 2. I cannot tell you with respect to each other where they are located.
Well, I'm talking about you wouldn't be able to compute how far apart they are because their clocks are different from each other.
No, that I would.
So what's the minimum number you need talking to each other to solve?
To measure just the distance between 2 nodes. I'll show you the arithmetic of it offline. But just 2 nodes can give you distance between 2. When you go to 3 nodes, now you could do triangulation. but you would have mirror symmetry. When you go to 4 nodes, then you break that mirror symmetry.
That's after the clocks are synchronized.
No, there's no synchronization of the clocks.
Well, then you compute the drift, the offset, right?
After the parameters of the clocks have been pulled out. Because that's what we are taking into account to get you the estimate of distance. Yeah, you had a question?
I do. It might be getting ahead of the slides, but
Please do.
one of the things is that when you're doing, when you're transmitting signal at such a high frequency, it's very dependent on the medium it's being transported through. So if you have like a change in humidity conditions, or
that will change the speed of light?
Well, not the speed. Right. We're talking that high. So it doesn't matter whether.
Not as far as I know.
Yeah, you're not sending light. Okay, I was.
Yeah, see, we are sending speed of light.
You're right.
Well,
right.
Yeah.
I don't mean to get too technical with it, but speed of light through vacuum is what you're assuming here, right? I mean, if it's going through walls, I think there is a certain amount of.
What is the variability? See, the basic issue that you have to raise is by doing that, what kind of variability you'd get. So how much inaccuracy you'd get. Okay? Yeah.
You do need because you make the assumption that when you timestamp, you're able to send the signal instantaneously.
Refraction is due to.
Or there is a constant delay. Any constant delay I can factor out. See, if you can make the delay constant, I can factor that out.
Right, but in most of the hardware,
Single mode or multiple fibers.
Well, I just.
most of the hardware, you don't have that constant delay though, right? You have other issues that are.
See,
For example, even if you wanted to sort of use the channels in the signal, you have a map which might incur.
so you don't do it at the max, you have to do it at the hardware level. And you're right that to get accurate timestamp, you have to go to the hardware level.
That's what I meant.
Yes, yes. Yeah, like this 1588 protocol of IEEE, there they do the hardware level time stamping, and there are special hardware that's built for that. Anyway, folks, any other questions, comments? Let's move right along. This is, as I was telling you, actually done in the basement of somebody. So this is his basement with the recreation area and stairs and bath and closet, and these are the measurements. And the largest inaccuracy that you see is at location number 7, which was here. The log unit was out here, and there is no direct path from here. So the signal had to go bouncing around. What we were measuring as the ideal or the actual measurement was the direct path. So compared to that, you did see errors in that, as you would expect. One of the other tests that I don't have the results here for, we did was we took this in an IKEA stores basement area where they had lots of pots and pans. It was their kitchen area, and the accuracy in this was about equally good. This is indoor overall measurement. This is the outdoor measurement, which again was done basically in this area where the layout looks something like this. The log unit is here, and these are the points at which we made the measurements, and that's how the accuracy comes about. This was roughly 95% at 13.3 feet.
The assumption on that one is that everything is line of sight, obviously. Is that correct?
No.
Everything on this test is line of sight?
No, what we are doing is measuring whatever happens to be.
If you had a situation where everything was line of sight,
Yeah.
so that there was no reflection problems,
Right.
what do you think is the major source of error in your system?
The time stamping ability.
And what is the variability in the timestamping mechanism? What does that do to it?
The one that we were doing here, it was very unstable basic clock. That was causing variability in our case.
So this gets back to that question. So, I mean, I've looked at a lot of oscillators. And so are you saying that the variability between oscillator A and oscillator B, or variability in oscillator A?
Oscillator A itself, because the way it was implemented was not very stable. We'd love to learn from you how to build stable things. Okay, this is the hardware limitation that we've got, basically. So, yeah, I'd come back and become your trainee. One thing that we did was a mobility evaluation, where somebody started along the distance path of the red line, and the green line shows how that was tracked, which for all practical purposes was pretty close. But of course, one limitation that we have with that is that you require special hardware. So one thing we tried was to go to the standard NIC, and these days Wi-Fi B, BG type of NICs have a 40 megahertz or 80 megahertz clock. And while standard calls for 1 microsecond accuracy, if you can get into the firmware, you can get the timestamp with that kind of accuracy. We did not have access to the firmware, but and even using the public domain device drivers that are there for Aethros chipset, and then modifying some of those, we could get some implementation up and running, which was giving 40 megahertz type of clock accuracies. And doing that, of course, we did not have the full details of the firmware. So as a consequence, some of the kinds of things that we were getting were like spikes of long deviations that were coming out, which were, I'm sure, due to firmware idiosyncrasies that we were not accounting for. With that, we were getting a 5 feet accuracy. Now this is interesting that 40 megahertz clock gives you 25 nanosecond clock tick time. So you're measuring distance with the 25-foot scale, 25-foot long pole, and you're getting measurement accuracies of 5 feet. Statistical averaging and other factors come into hand. But if we can get to more accurate, even 40 megahertz or going to 80 megahertz as most of the G and A type of chipsets are going to, we can bring this down to a couple of feet easy.
I still don't get it. I mean, if you need that support that we just talked about, right?
Right.
I mean, so even if you have this clock accuracy, you're not going to be able to get that other level of support, which is just a signal out right away instantaneously.
No, see, then there is a constant delay on that.
It's not, right? I mean, if you're going to use the Mac, you're not going to get.
I'm not using the system clock. I'm using the clock on the NIC itself.
I understand, but the NIC has to transmit the signal, right?
Right.
So it needs a different circuitry if it's not going to go through the Mac to transmit that signal as well.
Understand. The kind of thing that's happening is that on a beacon, it is putting out that timestamp.
And the beacon goes to the regular Mac. Today, the beacon is used to the Mac, so the beacon does not has the variability in it. That's why you actually miss beacon clock.
Let's talk offline. But I mean, if you can get us that, we'll show you how to get more accurate kinds of things out. See, otherwise you'd have to play certain kinds of games about putting the senders at particular ticks or something.
So, I mean, the time differencing of arrival schemes sort of have existed for a while, and the biggest issue has been indoors, has been post reflection and all the other stuff, but it's also been hardware costs have been quite large to implement it.
Yeah, see,
I was just trying to see that
lately, IEEE 1588 protocol people have been implementing special hardware for Ethernet drivers as well as some wireless drivers, from what I understand. And in that, one of the key things is to be able to timestamp. They have a separate timestamp circuitry that's in there, and because of the exact issue that you're talking about, what they do is at the sending time, they'll take the timestamp at the time of sending, and then in a follow-on message, send that timestamp out. So, I mean, in our case also, we don't have to put the timestamp in that message itself, because in the information exchange phase, we can take care of that. So there are various tricks at system level that you can play in some of this. Anyway, moving right along. So this is sort of location kinds of things, and these are some of the technologies that we have been working on and moving along. But another issue that comes up is that of time. And in that, I want to share with you some of this time technology. We call it Cyclone time technology. The basic issue is how accurately can we synchronize clocks. And some common characteristics of our techniques is that they are peer-to-peer architecture. The scheme relies only on local information that they can obtain from their immediate neighbors, converges pretty fast. But the key in this is the clock model that we're using, which I was also talking about in the PinPoint type of situation, where the real-time T is related to the locally measured time by this kind of an equation. And what we have here then is that, let's say that I have two nodes, and node A sends a message at this time. The subscript is the sender's ID, superscript is the clock ID. So nth tick was sent at that time, which was received at this time. N plus first was sent at this time, received at this time. Now, in the first algorithm that we have, there's a bunch of assumptions like all nodes are connected in that there is a path from any node to every other node. Transit time of message from node A to node B is fixed, which in certainly wired situations is constant. In other cases, we'll be relaxing it later. Each node is capable of time stamping an incoming message with its local clock to within a clock tick accuracy. Then each node is capable of sending a message at a defined local time to within a clock tick. And then if there is a variability in time stamping operation, this gets lumped into variability in the transit time in this case. So the goal here is to correct drift at all nodes. That was the first thing that we start out with. And in this case, each node sends a beat message at a time that is determined from its local information. Now this message, all we are sending there is an event, a marker in some sense. And each node to start with uses a constant number whose value is fixed at design time, let's say pi. So the way this scheme works is that node A sends pi A of 0 seconds later this one, pi A 1 seconds later this tick, etc. Similarly node B is sending, and these are received here at these times. This is just a graphical depiction of what we have. So our basic algorithm starts out that, mind you, whenever I'm using tau, it is strictly with respect to the local clock. All local clocks are free running with no adjustments being made to them. So at the 0 time, everybody selects some arbitrary time at which they send out. So then they send the first beat, this constant pi later. And the subsequent to that, what each node is doing is measuring on all incoming lines the time difference between the previous 2 beats, and then selecting its time to send as the average of all the intervals that it has observed in the previous cycle. So it sends the next time at its previous time plus this interval that it selected. If you continue to do that, what will happen? The interesting thing that happens, basically, I can leave the copy of slides so you can see, but what's happening here is that this number, the time of the next step, is simply an average of the time that I got from all my incoming ones scaled to my time clock. And this you can represent in matrix notation, that if I represent Aij as 1 over Kj, provided there are k such incoming lines on node j, then this is nothing but a stochastic matrix with all rows summing to 1. And what happens is that at each step we are carrying out this calculation. So this is nothing but a power method of calculating the principal eigenvalue and eigenvector for stochastic matrix that's known to be 1. And so as a consequence, the eigenvector becomes all same values. That's basically what's going on in here. So, yeah.
Is this guaranteed to converge even in a multi-hop network?
Absolutely. See, multi-hop doesn't matter because all I'm concerned about are my immediate neighbors. So as long as this matrix is connected, that's all your requirement is.
It doesn't matter if I'm the only one and I'm kind of between 2 blocks of
that doesn't matter.
peaks and I'm in the middle and they kind of converge to different values. And
no. See, because there is a single matrix that you're talking about. As long as when you are connected in the middle, you have two-way connections. So the information can flow from both sides. Now, clearly, the convergence rate depends on the diameter of the graph that you've got. So in that case, the diameter would be larger, convergence would be taking longer. But it is guaranteed to converge.
What can be said about the convergence? Like, can you?
What? It's exponentially converging.
Is it exponential?
Right. And converges very, very fast. I'll give you some numbers from some simulation kinds of things. Now, this works, and of course, this mathematics you assume infinite precision. So once you have converged, the value is constant, everything is fixed. In practice, you have to worry about finite precision. You also have to worry about if the transit delays become much larger than your beat time, then what is my cycle, n is your cycle, n minus k. there's that kind of problem I run into. So what we have done is developed it to the point that we have addressed all of these issues and done primarily through simulation, where we have clock tick time of 100 picoseconds, just arbitrary numbers that we are picking up. Cycle time, or the base time pi that I was talking about, was 125 microseconds. The basic idea was that this was designed in the context of a communication technology that we were developing, in which we wanted to replace essentially SONET type of stuff. And in SONET, they are sending 8,000 frames per second as a base rate. So we wanted to go to that one. That's why we picked some of these parameters. Latencies we collected as random, tried different technologies like chain, star, random, drift rates of plus minus 100 parts per million. Converged in every single case that we have simulated to date. On convergence, the jitter of the time was no more than 2 clock ticks. And why 2? Because if the actual converged value is not a full integer, then there will be some accumulation that will take place, and as a consequence it goes 1 up and 1 down. So that's how you get this converged value to 2. And we have let it run for 12 hours of simulation time, and no accumulation of jitter occurred. And after that we were convinced that any arbitrarily long period of time is not going to cause any further jitter. Here are some values, I mean how fast we achieve convergence, like this is the number of nodes in star, chain, bidirectional, random topologies, and typically this is in 60 seconds, 15 seconds, etc. We get the convergence. Even on a 1,000 node random network, the convergence was in about 31 seconds. And this was an arbitrary convergence point. I mean, we are not continuously monitoring when is the initial convergence point in that. And the basic criteria that we had was that after we claim that we have reached convergence, the variability in the cycle must not be more than 10 clock ticks. We were getting about 2 clock ticks at this point. So the effect of perturbations, we varied transit time by 10%. No more than the transit time change was observed and stabilized very fast. Clock drift rate again varied by about 10%, again stabilized very, very fast. These are the transit delays with maximum latency kind of curve. The convergence, it converges, but convergence rate does go up as you go to the latencies as high as 1 second between a single hop. We are not talking about multi-hop, because all our calculations are across a single hop kind of situation. The latency perturbation numbers, as we go to these different values, it remains the jitter that you get, cycle time jitter, is very, very small. Drift rate perturbations, similarly very small numbers. The implications, in this scheme we can achieve clock synchronizations to a common cycle value of pi star, and the local value will be different because it's measured with respect to the local clock, but the true real value is constant across the whole network. Now the interesting thing in this is that if in this network we take one node that has atomic clock and don't change anything in that, it doesn't do averaging, everybody else will converge to that value, guaranteed. So the scalability, it can, we believe, be scaled to internet scales. Now one thing that we have done here is adjusted for the drift rate. The time offset can still be there. So for that we have extensions to this where we have clocks. We assume that there is a virtual clock with parameters alpha star and beta star, and the key idea is that can we calculate at each local node enough information about alpha star and beta star that from their local time they can convert their time to the virtual clock time, and that everybody will do that in the same way. How much time do I have? When is somebody going to come and knock on this?
How much time do you need?
About 6 hours will do. No, about 10 minutes. Okay, I'll speed up through then some of this part. Again, I mean, a lot of this, I'll be glad to leave the slides and send you more details, get in touch with me. But this is interesting stuff in the sense that I have a lot more details here. To start with, we are assuming bidirectional times, and the key idea here is that, again, following the same kind of principle, except that what we are saying is that in this case, beat message, instead of being just a time marker, contains some information also, like the converged cycle length, current cycle number, and some of these time values. And based on that, then we can go to the multi-node operation and come up with a way that each node can calculate time on a common time base. And this again is applicable to the internet-wide type of scale. So on convergence you get that, and that's how local time can be converted to the virtual clock time in this kind of situation. Simulation results confirm the claims that we have. We are working on prototype implementations using standard NICs on some of these, and let's see how this goes. These are comparisons with different clock synchronization schemes, including IEEE 1588, NTP, GPS based, TTP, various schemes. So that's the comparison of this clock synchronization. Anyway, let's come back to the story that I started with, which is Rover, which is using the context where different users and situations have different types, groups, different environmental factors, network setups. What we are trying to do is to come up with situational awareness kinds of things, and a lot of people have been doing that in terms of information fusion. So generally they try to fuse similar pieces of data. Here the issue that we are trying to raise is that without reinventing the wheel, can we come up with an integration platform which supports a variety of technologies? And we have distributed servers in which information can be combined and distributed. So this is the basic architecture that we've got, and each of these can be a Rover server with whatever kinds of things that we have attached to them, and then we provide a common base on which we can come up with the common situational awareness. I'm going to skip over the scenarios for this audience. The current, we are using Microsoft's .NET platform. We have single Rover server with multiple clients. Distributed one is in the process of being tested. It's an RDF based messaging structure, an asynchronous networking paradigm, TCP only. Developers basically like handlers for processing. In the messaging structure, one of the things that we are not trying to optimize the amount of bits that we are sending. So each of the message contains three distinct parts: an action, a context, and content. And so we can come up with a common notion of context or do the merging on context for this information. What I was showing you here was just one facet of Rover. This is basically what's underneath, and this allows us to integrate a large variety of information and information sources. We have integrated voice over IP, audio and video technology, internet services like RSS feeds from Yahoo for news, weather, web searches, sample shopping applications we have integrated on that, dynamic code downloading and loading, tracking and tagging of location. This tracking and tagging is interesting in the sense that we utilize our technology for location, and we can place information about certain location, can attach code to a tag which executes when certain conditions are met. So these can be very active tags which can carry out a variety of functions on that. Next, we'll expect tagging to include more than location, like time, users, complete space, other such kinds of things. Distributed in multiple Rover servers are the next thing that we have to test in this. Ability to handle UDP streams. We are getting some VoIP type of things done, but have to be integrated in more tight manner. And more integrated information from more sources. On the concluding, I'll just put this one up, that this is the framework within which we need to come up with the common integration platforms, because I personally am convinced that the biggest challenges that we face for tomorrow is our ability to integrate complex, diverse, divergent, distributed sources of information, processing capabilities, etc. And how to make that user's interaction experience, shall we say, non-painful, is the best, most positive thing I can say on that in today's environment. that's how you can get hold of me. And thank you for your patience and bearing with me. Any questions I can answer? Thank you. Yeah.
Are you familiar with a company called Rosum that does
Yes.
TV signals?
Yes, I am familiar with that.
Can you elaborate more about what they're doing? And
Basically, from what I understand, what they have is in any market they would have the signals that they're getting from the. They have the TV signals, and TV in their subchannel have some timestamps. So then they're measuring the distance to the TV transmitter locations by again measuring the multiple timestamps. So they receive that signal timestamp locally, see the difference of timestamps, and using those kinds of techniques.
what level of accuracy did they achieve? You know?
Last I heard, they were between 10 to 30 meters or somewhere in that ballpark. But my information is not very current; it's at least a year old. Yes, sir.
I missed the beginning, so you may have covered this, but what assumptions are you making about trying to establish common time amongst these devices? Because, for example, if you have a local AM or FM radio station,
right,
you can do that relatively easily.
Right.
Or if you plug them in, you can phase lock to 60 hertz.
Right.
So it's sort of like, what are your base level assumptions?
My base level assumptions start out that I want timing accuracies down to much better than a microsecond, more like in a few tenths of nanoseconds or
in a desert, where there's no radio signals, or anywhere in the world, or in cities, or what other infrastructural components can I assume?
It depends on the kind of technology that you're going to be using as to what kind of assumptions you can make about the infrastructure. In most of the kinds of situations that I'm talking about, the infrastructure is some sort of deployed wireless capability, whether it's Wi-Fi, whether it's some other kind of thing. So I'm assuming that there is some means by which you can do some communication. See, when you go to the desert and you're relying on GPS, there is some communication still available. So it's basically that kind of an assumption that you're going with. Okay?
Okay. Well, thank you very much.
Thank you.